I happened to learn a couple of 2 talks ago, we are supposed to tell something about ourselves. Yeah, and I decided to actually get due to this book. So this book was published in Soviet Union in 1986, and it contained a bunch of publications of famous Western computer scientists. And this book happened to be in my house somehow, no idea. I'm quite sure my parents never read it, never opened it. But once I glanced through pages of this book, I realized that almost every image there, published how many, 40 years ago, either influenced stuff that I was doing during my life or has a chance to influence the future course of my career. So this is one of the pages that really fascinated me as a kid. This is actually a chapter that was translation of one of Stephen Wolfram's articles on cell automata, and those looked beautiful. And actually, when I first learned programming, I implemented some of those things in Turbo Pascal at school. And actually, my first public talk, which was program kids who are interested in programming, a conference in our hometown in Urals. I was presenting this stuff, and I don't think I managed to explain what's going on to people back then. But actually, these are just a few pages, I made screenshots. So the idea that you could put physics in a simulation and predict stuff about the world, I learned about it from that book, although I don't think I could understand the equations or anything. But also my interest in computer graphics and ray tracing, these are the pages from that book. And these, I realized, that's where I got interested in that. But even stuff language modeling, artificial intelligence, they are also relevant sections. And even
what's the name of this book?
It's called Modern Computing or Modern Computer. But these, I can give you a list of actually original publications. So these are all translations to Russian. Yeah, but even these, it's about robustness of computer memory to cosmic rays. But actually, this also was about layers, how digital circuits are organized into these layers. First layers are transistors, and then you have interconnect. It had even isometric diagram on a different page. And I'll also talk about this as well, because that's what I'm most interested in right now. But then I then glanced through my YouTube channel, and this was my first video. I made it in 2007, and it was a landmark for me for a few reasons. First, this is actually a cell automata. It's a Lattice-Boltzmann model, which is very good at modeling liquid, gas or liquid dynamics, especially in terms of complex boundary conditions. And also, this was the time where I first learned about GPU programming, first shaders, and then CUDA. CUDA came out in 2008, so it was the right moment for me to learn about GPUs, and that shifted, changed my perception of programming. In a way, I had a similar magnitude of shift in my perception of programming last year. I'll talk about later. But then another, I guess, second or third video from YouTube channel, and I realized, this is due to that page from that book, also cell automata on hexagonal lattice. But then this says 2011, but actually this video was recorded in 2012. So there was a moment I was super interested in computer vision, participated in Google Summer of Code, and actually Google happened to play a huge role in my early career. So these Google Summer of Code payments, the first $5,000 spent to trip to New Zealand with my future wife. The second payment was my first car. Yeah, but these are stuff I was experimenting with real-time computer vision. It was before deep learning, and yeah, these were Python samples for OpenCV computer vision library. But now this is the video I made like recently, but it's a tribute to something that happened 10 years ago. This is about stuff that brought me in research when I joined Google 10 years ago and started playing with deep neural networks. And like one of ideas was, what if you like just give network an image and ask it to amplify whatever patterns it sees there by propagating to input space. And that year I happened to flood the internet with dog slugs. I don't know how many people remember this. Yeah. But actually, this happened to be like one of the first moments where general public heard about deep neural networks and their generative capabilities. And like fast forward 10 years, now this stuff is like very hot. So these were like the first science, and these dog slugs like coming to be nightmares. Actually, this was made the moment, the night I woke up from some weird dream as if someone entering the house, and I'm like, okay, it's 2 a.m. I don't know what to do. I don't want to sleep. Let's code the experiment that I wanted to, was on my mind for a few days before, and suddenly I got, I got this. Yeah, but then then this is from stuff that I'm working on now. It's neural cell automata, and the idea is, of course, take lessons that I learned from neural network experience, that those things are quite flexible, take neural controllers, put them in interpolated environments, and evaluate them with some global system-level objective function, and backpropagate gradients all the way from the objective function. Why is my behind me just freezing? To controllers. So this was the core idea, and there were some successes of this idea, some failures, but yeah, these were our first, one of the first neural cell automata models with texture synthesis and pattern growths and MNIST classification. Okay, this is a long video. But what I really wanted for a long time is some physical, real-world implementation of these ideas. And there are a lot of potential substrates. Of course, ultimate substrate would be to implement these control structures in genetically engineered organisms, so that you could have like plants with specific beautiful patterns on their leaves and stuff. But actually using electronic and circuits, circuits is one of the obvious candidates, and I spent quite a lot of time trying to lay out this computation in a circuit way, something that looks like electronics. And electronics is not deep neural networks. Deep neural networks aren't particularly friendly to map into electronic substrates because they're very dense. Everything is connected to everything. But actual circuits are quite sparse, actually. By the way, speaking of sparsity and actual circuits, let me show. This image happened to be on the behind the bed in the hotel I stayed in. So I couldn't think of a better better background for the first slide, but unfortunately I forgot to say it, so I need to. Okay. Now to circuits. So this is one of the demos that I never end up publishing, but always show to people. This is a texture CA, but this is implemented in a way that is friendly to So if you zoom in, you see that I manually routed connectivity between cells, and actually, does it have a laser here?
Yes, the top button.
Yeah, okay. So, every cell has 12 state registers that are those dots, and then there is a parameter matrix, which I didn't visualize properly, and there is some connectivity, so every cell is connected to left, right, top, bottom, and and these pass through this connectivity matrix, and feedback loops update the state. So it's sort of an analog circuit. Later, after I designed it and I started to learn something about analog computing, I think these are like operational amplifiers, like wired as integrators. Okay, but then I wanted to learn how, well, at some point I wanted to learn how actual computing works, and this is when I like discovered Tiny Tapeout and these open source silicon design projects. And this is a video I made like this year. It's called Digital Heartbeats, and it shows like this is a circuit I designed, then it shows a few circuits other people designed, and it starts with Verilog. Logic description that is like tooling takes a Verilog and transforms it into layer masks, and it looks like this. So there is arrangement of like standard cells, and then there are a few layers of wires, very, very messy. And then I made this gate level simulator that would show the, like there is a clock ticking there, and we see how wires change their state after every clock edge. And this particular circuit generates a VGA signal of this one-dimensional cell automata. And we see there is a shift register that contains the like last line, so you don't have memory. It's a very, very like restricted to like one tile. That I don't have enough memory to store the whole frame buffer. Actually, I'm storing the last line, and this generates the image by tracing the beam. So it needs to feed data to VGA as fast as the array scans the screen. So and when we accelerate, then we see like which wires flip most often. This clock tree, of course, but also data lines between the these shift register cells. This is another like circuit that draws this nice cat, and actually it has two parts. This one generates music, and this one generates imagery. And so if we slow down, we start seeing like clock tree that distributes the signal. And also, it's kind of interesting, like first how messy these actual like circuits that our computers use are, and also how they are sort of reminiscent of spiking neural networks. Actually, when you like change the like on clock edges, you have these cascades of flips, and actually single wire may have like there is this transient state where wires find new stable states, and every wire like can flip multiple times depending on like how, say, like if it's connected to like inputs that are separated by some like delay. And this was sort of artistic project for me, but also I wanted to learn to understand the process, like how my Verilog became this. And I started like digging into how like tool chains work, and one of the things I discovered that actually this is how like some stages of circuit synthesis work. So they like take Verilog. There is a lot of like hundreds of steps. But some of this, that you take Verilog, you can synthesize the like graph first of abstract gates, then you map those gates into like library of standard cells that are available in your particular PDK. That is super secret stuff that on all foundries keep very restricted, and then you form this graph, and then there is an actual gradient-based optimization process that finds like placement of those nodes on the chip surface that like minimizes some proxy for wire length. So first you like find this approximate placement, and then you actually synthesize wires that link everything together. And also these red are like stand macro blocks, which are like hardened things that you can't modify. Usually these are SRAM buffers, like memory. But this sea of gates is something that looks like super random and super organic, and is super messy. And when you look at this process, really like something alive is going on there, and this is what powers all our computers. This is what,
So this thing is, what are you looking at here? This represents like the full processor, or?
Well, not necessarily processor. This is some chip. Some chip.
Okay.
Some chip. It has some macro blocks that are like large cells that are very carefully designed, that particular foundry knows that they can make them. And there are small like standard cells which are basically gates, and that are like more that are connected somehow, and tool needs to find the place everything together so that wires aren't particularly long, because actually like to move to send data, you need to charge particular wire to some voltage, and the longer your wire, then more charge you need, the more electrons you need to push. So, speaking of masses, I guess you may know this photo, Rosenblatt perceptron. Actually, there was this idea in computing when you start with a mass and try to make this mass do something, rather than get a mass as an artifact of your thought. Then there were those two papers I learned about them last year by Felix Peterson and his allies in Stanford, and the key idea there is you start with a mass. So you organize gates in layer, but wire them randomly and fixed. You just wire them, fix, and then you compute assignment for functions these gates compute. So the way you do this is actually gradient-based optimization. Although boolean gates doesn't look particularly differentiable, but actually they're quite differentiable. And what they do is they relaxed the no laser for me. Okay, it's weak. Anyway, relax the Boolean function to its representation that assumes suppose you have two independent probabilities for A being 1 and B being 1, then you can easily express the probability of the output of a particular gate to be 1. And also another trick, you need to initialize everything at the beginning to have a pass-through, so that every gate simply skips and copies one of its input to its output, and this greatly improves the training performance. So and they do to assign the role or to every node, they do softmax over 16 possibilities for every node. So I simplified things a little bit because instead of using 16 values, 16 parameters for every gate, I was optimizing lookup table directly, and there was a very simple way to express this in a differentiable programming framework. So essentially, you have lookup table, and then you process inputs one by one, and at every stage you reduce the number of your entries in your lookup table twice by linearly interpolating between odd and even elements of your lookup table given corresponding input. So first you process first input, linearly interpolate between even and odd, get twice smaller lookup table, and then repeat the procedure for the next input. And this way you can easily scale to gates that have more than 2 inputs by just stacking more and more layers here. And so this is what Jack's version of this computation. And here is initialize everything with pass-through. And then there are two versions of this decode. Decode soft takes logits and produces probabilities. Decode hard, just threshold at 0.5 level, and your smooth relaxed circuit becomes actual digital circuit that you can synthesize and tape out. Then actually I started looking at gradients of Boolean gates, and even in fully saturated regime, actually you can easily express partial derivatives of output over individual inputs and values in lookup table. For example, on the top you see XOR gate. So these are inputs, these are outputs. This is a 3-input XOR. So it's 1 when you have an odd number of ones in inputs. And you see that this is the gradient, so derivative of output over corresponding input for the corresponding combination of inputs. And we can see, for example, that in case of 0 inputs, this gradient is 1 everywhere, because it means that flipping this gate will switch the output from 0 to 1. Or, for example, sometimes you have negative gradient, which means that if we flip this single bit, output will go from 1 to 0. And or like for majority, you can also have this like similar structure. For example, here all gradients are 0 because flipping every single any bit will not cause gate to flip. And you can also do this in different, this relaxed setting. So here, lookup tables are still fully saturated, but inputs are like not 0 and 1, but 0.1 and 0.9. And you see that you start to get like some values, some non-zero gradients in lookup tables. You start to get like more relaxed values in the gradients. But there is one caveat that the gradient, the true Boolean gradient of the whole circuit, and the gradient that you get from backpropagation through the individual gates are different things. So, well, apparently they're correlated. Maybe this is the reason training works, but this backprop doesn't give you like the actual true gradient. Well, I didn't make a slide to explain this in here, but the problem is that this formulation assumes that inputs are not correlated. But if they're correlated, then this assumption is violated. So that's the reason. Okay, so here I'm going to talk about toy tasks. So my toy task, this is my set. These are problems that have 8 inputs and 8 outputs, and so every column corresponds to a single combination of inputs, and 8 shows outputs that network's supposed to return for a corresponding input. So identity means simply copy the inputs. Gray code, convert the input to corresponding gray code. 4-bit adder, take 4-bit first 4 bits and add them to last 4 bits. Population count non-zero bits. Basically count once. Multiply 2 4-bit numbers, and then 2 memorization tasks. One that has some structure in it, and another with just memorize noise. So let's see how it trains. So this is for 2 input gates, and on the top we see plot for the soft loss, which is the relaxed. This is the thing we are optimizing, and this is the hard loss. This is not the thing we are optimizing. This is what we evaluating. So we harden everything, threshold all the gates, evaluate them as if they're Boolean circuit. And to me, quite a few surprises. So first, this thing trains, and it trains quite well. And for simple problems, it can actually find perfect solution. Here, number of parameters, I forgot to put it on the slide. Totally, there were all lookup tables combined had between 8 and 9,000 bits. So basically, you need to remember 2,000 bits, and all gates combined are 8,000. Well, I think 8,800, something like that. And we see that also apparently the simpler the problem, the easier, the faster optimization finds it. Also, hard loss really correlates very well with soft loss. So minimizing one usually makes the circuit solve the another, and here only the noise memorization problems couldn't be satisfied. And this process, optimization, is completely deterministic. And actually trajectories are very smooth for some problems. And sometimes there are jumps, but for some problems it's really continuous optimization. Then with 4 gates, so okay, let me previous. In same axis, 4 gates train even way better. Here I adjusted, given my every gate has 16 parameters, extent of 4, I adjusted the number of layers and number of gates and layers, so the total number of parameters is approximately the same. And with 4 gate inputs, optimization managed to even memorize noise, in a in some of the optimization runs. So, like empirically, there is this factor of 4 of overhead which you pay if you don't control the connectivity. And there is something to say about it, because there is something about 4-input lookup tables. Because if you look at FPGAs that are like mostly like most popular FPGAs today have a 4-bit lookup table as a primary building unit. Of course, they like every logic cell has like 4-input LUT, and then a few like carry input, a few like flip-flop, and they also have a bunch of hardened logic like multipliers and stuff and memory blocks. But focusing like, but actually, if you look at the like floor plan of like more FPGA, then those logic blocks is a smaller part of a smaller part of the chip area, and most of the area is connectivity, is routing switch boxes that you can adjust like program to connect those LUTs. And apparently the price that you pay for if you say that like I can't control connectivity, it's given to me, is not like prohibitive. And also, there is something about this random connectivity, like our manufacturing processes are designed around being able to route every wire precisely where it's supposed to go. But what if you have some sort of manufacturing process that is like developmental growth? I don't know, maybe some cells that like split, and then connect somehow. And there is definitely some factor of randomness in such processes, and if your manufacturing process is like this, then this price is like reasonable. Yeah.
Just a question. So in these tasks, what is the input to the circuit? So they need to reproduce the image, but
yeah, 4 bits.
Okay.
Yeah, well, sorry, 8 bits. Eight bits that are treated as an index of a column.
Okay, I see.
And then, demo time. So
I have a question also.
Yeah.
So you said there is a like 4x extra cost that we pay if we use random wiring.
Yeah.
Like how does that rate change if you allow for larger lookup tables? I mean, basically, like instead of 4-bit gates, you allow 8.
I didn't try. But what I know that 4 input works better than 2 input. That's sure. So I would expect larger lookup tables work even better. But with larger lookup tables, it's like, well, basically the larger the look. Of course, perfect lookup table could be just take the 8-input lookup table and the 8 output and memorize these 2048 values. But this is not particularly interesting from like perspective of design, because like you're like sneaking your complexity. Actually, you will have a like huge SRAM with these encoders, decoders, and it's a very, very like fine structure. Okay, let's run this demo, because I wanted to see like intuitively. What does it look like when you play with this thing? So here at the top we see 8 inputs. I can flip individual inputs, or I can select a combination of inputs by hovering this image. And these are 5 layers. And here I like cheated a little bit to simplify wiring. I grouped gates into groups of 4, and every gate in a particular group shares 4 inputs. So like these 4 gates, they have same shared 4 inputs, and when I hover I can see lookup tables corresponding for individual gates, and they have like different lookup tables and they produce different outputs. So with this configuration, every input has the same number, like if they have same number of gates, they have same number of outputs and inputs. There is like nice beautiful symmetry. I think like sometimes think of every like this group is a single chip that has 4 input wires and 4 output wires, and 64 bits of memory inside of it. And then what we can do, okay, we can shuffle wires, and here at the top you see optimization. So blue is the soft loss, and orange is a hard loss. And every time I shuffle wires, like optimization constantly running at the background, and every time I shuffle wires, sometimes it's difficult for the circuit to like recover the last bit, but usually it manages for multiplier task. does it quite well. I can also what I can do, like switch a task. So like 4-bit adder is very easy to satisfy, or like say copy task. If I like satisfies it almost instantly, then I can use like a simple stupid heuristic to find gates that are not used and like mask them out. So actually we see that the number of gates that a circuit uses is dependent on problem complexity, and here we like see the paths that are used, that the optimization found to propagate each of inputs to outputs. But actually we can like reset gate mask, and for more complex problem, for example, for adder, okay, let's reset optimizer. Like you will see that there are also a lot of there are more gates used, but I can actually knock out individual gates even after I did this pruning. And sometimes we see there is like a spike of errors. So when if I disable training and knock out some gate, let's knock out this gate, we see that like whole first bit is incorrect now. And if I'm enable training, then usually, well, okay, this one time it managed. So yeah, it managed to recover. So we found some different path to solve the problem. For more difficult problems, okay, let's reset gate mask and select this text memorization and reset gates optimizer. Let's wait for it to satisfy. So we have a few error bits here and there, and now it's solved. And if we mask unused gates, then this heuristic finds very few. I can still knock out individual gates, and if I'm not too harsh, usually it manages to recover, although recovery takes longer. So when I knock out a gate, I just clamp its output to 0. I can also edit, okay, let's reset gate mask. And I can also edit the objective at runtime by typing stuff here, and we see how the circuit like adapts to new situation. All you need zeros and evolution. Let's try harder. By the way, this network is smaller than the network that I was used in experiments that I showed before. It has 4,000, well, a bit less than 5,000 parameters. And but when I ask it to remember like harder task, let's try to reset everything and memorize noise, then we see that like it's loss is slowly going down, but it couldn't, like it's stuck at 50-40-ish errors, which are shown by these like red pixels here. And now it's 33. But if I change so now probability of 1 and 0 are the same. But if I change the probability, say like 20% of pixels are like ones, and the rest, you see that like here I compute the entropy of the resulting signal. And a rule of thumb is like more or less holds. So if entropy is approximately 4 times smaller, I don't know, for some reason, for this demo works better than the computational experiment that I tried in bulk. I suspect that the reason might be as ridiculous as difference in precision between CPU and GPU. Yeah, that's unfortunate. But in this demo, usually when I do 25%, and especially if I reset the optimizer, usually it manages to satisfy the problem after some time. So, which means that in this demo, it's about like 3 times. Overhead is about 3 times. Okay, what else can I do? I can try to restrict the connectivity, and usually the better things mixed, the better it works. For example, here I can say like that my gates have some degree of locality, and usually it's pretty detrimental for the performance. Although for this task it worked. I can also mask unused gates, and here population count only needs first 4 bits. That's why like this part is not used. But actually, if I have like a same multiplier, reset gate mask, reset optimizer, let's see if it manages to satisfy. So with this restricted connectivity, where every wire is connected to a previous layer wire within a certain range, oh, it managed. Let's mask unused gates and see. Probably earlier bits, like first bits, are easier to compute because they depend on fewer previous bits. That's why we have less gates used in this area. Okay, then, so this is the demo.
You have 13 minutes.
How many?
13.
13? Oh, it's more than enough because I'm almost done.
Great. I will have time for some
so, then another experiment is this, like during training, I use floating points as this proxy for bits. But what if we really restrict ourselves to using boolean signals, at least for forward pass? So here, after like running a layer, I binarize it, and like on forward propagation, I send bits, but on backprop, I treat it as if they were not binarized. And interestingly, so training takes way longer, but nevertheless, in this regime, it's possible to train a circuit. And what's also interesting that in this regime, training loss shown as blue is higher than the loss that you get if you actually quantize the circuit. Then another experiment is with this memory memorization. I just like did today. I wanted to have some quantitative graphs to show about capability of random circuit to memorize signals. So this is noise memorization, where a circuit needs to remember 2048 bits, and in total it has 4000 like something bits. So this plot, this below shows the entropy of signal divided by total number of bits in the circuit. And in this experiment, and these 3 plots is like I ran 16 random seeds where I randomized both circuit connectivity and pattern it needs to remember. And when this ratio was around 1.2, all 16 runs converged perfectly. I trained for, I think, 1,000 or 2,000 of steps. Then below like 0.5, so like most of runs converged. And then like the higher you go, the more like error bits you have. So this is the when you use 0.5 probability, which corresponds to like 0.4 something ratio between entropy, and total number of bits. And at this point, you can't remember like around 16, 17, maybe 100 bits in your signal. So you still remember most of them, but some of them, like, you can't remember correctly. Then we had a student, Pietro, who applied this. He used the original formulation without lookup tables to and say setting, and it was like quite a pain to train, but he managed to train a few CAs. So like someone's simulate mimic a game of life, just to see if we can as a first experiment. Then some were like a pattern generation, and some was very very simple circuit that does this checkerboard, but it starts from the boundary, and actually if you analyze the circuit, it's circuit recurrent, repeated in space, but actually it found a feed-forward solution. And the architecture here is that you have a perception phase where you apply like you have a number of channels, and for like these channels you compute some function. Like first layer is connected to center and one of your neighbor cells, and like apply some logic function to these, and then a bunch of like randomly wired layers that produce the perception vector, which is concatenated with like your own state, and you have also a random circuit that produces the your new state. So there is no like a residual part, you just compute your new state. And interestingly, like we managed to train some sort of non-trivial rules, like this checkerboard, or even something that is like pattern generating. But this is like the beginning of this work. So there was like a lot of things to try. Actually, there are also experiments where like people try to learn connectivity, and this produces way more compact circuits than random connectivity. But well, random connectivity has their own like interesting properties. Yeah, and this is all.
I think, yeah, we have like 5 minutes for questions, 6 minutes, and afterwards we should probably go towards the metro. So any questions? I have a question. When you mentioned this entropy limit, like you say that, for example, if it has 25% of the entropy of your number of parameters, I guess, yeah. This is the comparison, then it cannot learn. I guess probably a better measure would probably, it seems that your training model maybe measures somehow the homograph complexity of your pattern, right? So for example, I don't know if you tried to generate a random circuit to generate these random bits and then fit that. Probably that is learnable even at higher entropy in some sense.
Random circuit that generates...
Right. Instead of generating noise, you generate this noise by choosing a random circuit, so it's a lower homograph complexity noise.
Well, I wanted to check out what happens if you initialize gates with like just sample random circuit.
Exactly, yeah.
And here, okay, if I disable training, disable showing errors, and there is this randomized gates button.
Right. So if you,
so these
so it's very...
Yeah, so these are like, so here I realized that like if I set probability of zeros, of ones to 0.5, like in every gate, so I just sample all lookup tables randomly. Patterns weren't particularly like, well, they were too noisy, but if I decrease probability, so here I have, I think, 0.2 or maybe 1 probability of 1 in lookup tables, then patterns start to get sort of structured. And like okay, let's keep like this is like wires, and then let's shuffle shuffle wires. Okay, these are like same gates but different shuffle. Sometimes I like spot something that resembles like characters. Yeah.
Interesting. Okay. Yeah.
Okay. Yeah. Then
So yeah, no, that was just my question. Is I guess that. Probably, I mean, entropy is equal to the homograph complexity when it's actually random noise. So probably,
Another experiment I did is tried to like, what if you fit on a part of the training samples? For example, you take 8-bit adder, which takes 16 bits, and like sample some fraction of parameters. Adder didn't work particularly well and didn't generalize particularly well. But another circuit that was some formula, like, you know, there was a bit cup, like XOR bit bit carpet patterns, which you take index of your like X coordinate, take X is index of your Y coordinate, XOR them, and then like draw white pixel if the this resulting number is divisible by some prime number. And this, this sounds arbitrary, but actually there is like a whole like group of people in the internet. I can try to find it. It's called XOR bit carpets. Alien XOR. So well, images look. Where am I?
It was Shader Toy, the first one.
Yeah. So this not the best one. Like really not the best one. Let's try to find something better than that. Okay, bit carpet. bit carpet. No. It's not the carpet I was looking for.
Unless there are other questions, maybe.
Yeah.
Yeah, if there are other questions in the meantime.
I had one meta question. Is how the hell did you visualize the the circuits before and this thing? But it's not directly about the topic. So if someone has a specific question,
How I visualize.
like both the demo and like the circuitry that you were showing
Okay.
earlier.
Circuits I was showing in the video on YouTube. Swiss jail. This is unfortunately the library is so poorly designed that I'm the only person who's using it. But it's quite capable, and you can implement like so. For example, this like wave simulation. If you look at the code, it how many like 71 line. So this toolkit allowed me to express various. Things quite concisely, but I think I know how to make it more usable. Like I'll try to like split it into separate components. But so this is how I do visualizations for web. But there is also this is one of these bit couplets. Yeah, you see it, beautiful. And actually, this is the equation.
That's it.
Yeah, and there are other like you can like say try this one. Or try this one. So, okay. Then another thing is let me shout out about Dear EMGI. So this demo, I wanted to like try something new, and I finally gave a try to immediate GUI programming. So there is a project called Dear EMGI, and this is the approach to designing graphics user interfaces. Originally, it's like C-based.
It's also in Python?
Sorry? So
it's in C++ or?
It's C++, but I'm using a Python wrapper. But
Sorry, that's fine.
the philosophy is about like instead of maintaining complex data structure in memory that contains information about your layout of your elements and updating them when your state changes, you just generate every graphics user interface from scratch on every frame.
Okay.
And given that that is not as bad as it sounds, actually given mostly it's used in computer games where you redraw everything, every frame anyway. But actually this leads to surprisingly concise and expressive way to like model your graphic, like quite complex. So like these are examples like of graphics user interface people do with this stuff, and it's like super
That looks nicer.
lightweight, compact. So Dear EMGI. So this is a like whole philosophy about designing graphical user interfaces.
All right, we should really go. We can keep talking after, but thanks again.